Hello and welcome to our presentation about the Boeing 737-200 pneumatic system, presented by Laurie Blackburn, Kairos Meany, Aidan Gallagher, and Jan Mumtaz. On the next video, we will be covering the following sections: System Overview, Pneumatic Operation, Indication System, Redundancy, Maintenance and Servicing, Troubleshooting, and Case Study/Examples.
Boeing 737-200's pneumatic system supplies compressed air from the engine's 8th and 13th stage compressor bleeds, APU or a ground cart to a pneumatic manifold. This air is used for air conditioning, cabin pressurization, engine starting, and wing thermal anti-icing. The 8th stage bleed is the primary air source, with the 13th stage bleed supplementing when demand increases. Before reaching the manifold, bleed air is cooled by a pre-cooler system using engine fan air. The system features thermostatically controlled pre-cooler valves and air-to-air heat exchangers, operating automatically when engines are running. Pressure and temperature are monitored via pressure transmitters and over-temperature switches, with readings displayed on the cockpit overhead panel. Over-temperature trip lights activate if bleed air exceeds 490 degrees Fahrenheit, automatically closing the affected engine's bleed valve. The system also includes an air cleaner subsystem that removes impurities when engine bleed air is used on the ground or with flaps extended.
First, we'll be looking at the 13th stage modulating and shut-off valve. There's one for each engine and it's located upstream from the pre-cooler. See on this diagram where the 13th stage modulating and shut-off valve is located on the engine, circled in yellow. Diagram of the 13th stage modulating and shut-off valve. The valve is used when the 8th stage bleed air is not enough to meet demands. For example, if both the air conditioning system and the anti-ice system is in operation, then the 13th stage modulating and shut-off valve will need to be used to regulate the flow of the 13th stage bleed air for the system. You can see in this picture the valve has an actuator that is divided into two pressure chambers. One is an opening chamber that is connected to a pressure regulator, and the other one is a closing chamber which is connected to the pneumatic manifold downstream of the pre-cooler. The diaphragm assembly uses a connecting rod and a linkage to operate the butterfly valve. In operation, the pressure from the pressure regulator will be supplied into the opening chamber, which is where the pressure on the diaphragm will overcome the spring and move the butterfly valve to the open position, which will allow 13th stage bleed air to flow. The downstream pressure will be sensed in the closing chamber and will then close the spring, resulting in the butterfly valve closing. Here you can see the opening chamber in green. Here you can see the closing chamber in red. When the control pressure exceeds 7 psig, then the 13th stage modulating and shut-off valve will modulate. When there's a differential pressure across the valve, then it will move towards the open position. The maximum pressure that the 13th stage modulating valve can supply is around 45 psig above the ambient. If it exceeds this, then it will start to close. Next, we'll be looking at check valves. 5 check valves are provided in the engine bleed air distribution system. 2 check valves are provided at each engine, one in each 8th stage manifold to keep the air from entering the 8th stage engine ports during engine start or from high spool bleed. The 5th check valve is located in the APU supply duct to prevent engine bleed air from entering the APU. These check valves are highlighted in yellow. On the left is one of the engine check valves, and the one on the right is the APU check valve. These bleed valves are motor driven, electrically controlled, and of a poppet type. They'll shut off the bleed air from each engine. We'll be looking at the pre-cooler and the pre-cooler valve. This is shown in yellow on the diagram. There's one pre-cooler and pre-cooler valve for each engine. As you can see in the diagram, most of the 8th stage bleed air bypasses the pre-cooler. This is so the bleed air pressure doesn't drop too much and is also used for cooling. As you can see in this image, the pre-cooler is located below the engine. The pre-cooler is a plate-fin single-pass cross-flow type. It works by using the hot bleed air that has been ducted from the engine and is mixed with cool fan air. This reduces the temperature of the high-pressure bleed air to 188 degrees Celsius. The fan air that's been used is ducted overboard. In yellow is the pre-cooler valve. This valve controls how much cool air flows through the pre-cooler to regulate the temperature of the bleed air. This image shows that the valve has a fixed plate and a moving plate. The moving plate has an opening, so at low temperatures the holes can be covered to limit the flow of cooling air, and vice versa at high temperatures. A bimetallic element shown in yellow is used as a temperature sensing element. This controls the moving plate to then control the amount of cool air that's allowed to flow. The valve will be fully closed at 185 degrees Celsius and will be fully open at 226 degrees Celsius. At 254 degrees Celsius, the overheat trip is set to avoid trip outs. Next, along on the schematic, is the pressure relief valves. These are used to protect the pneumatic system from excess pressure. As you can see highlighted in yellow, there are 3 pressure relief valves in the pneumatic system. There's one for each engine and a third in the APU section. On the left shows a pressure relief valve on the duct forward of the APU, and on the right is an up close. The APU pressure relief valve relieves pressure at around 80 psi. Circled in yellow is where the pressure relief valve is located on the engine. The engine pressure relief valve will relieve pressure at around 106 psi. All 3 pressure relief valves operate automatically and will open when the pressure gets too high. They are spring loaded and set to their specific pressure, so if the pressure is exceeded, that pressure will overcome the spring force and open the valve. When the pressure drops back down, then the valve will close. Next along is the engine bleed air valve, highlighted in yellow. There's 2 and they are downstream of the pre-cooler. The valves are motor driven and electrically controlled when they are operated. This image shows the bleed valve control circuit. When the bleed air valves are operated, they will shut off the bleed air from the selected engine to the main manifold. The engine bleed overheat switch, that's circled in yellow, can also cause the engine bleed air valve to close if the bleed air temperature exceeds 490 degrees Fahrenheit plus or minus 10. A trip reset switch, that's circled in red, can be used to reset the engine bleed air valve on ground if it has been closed. Circled in yellow is the engine bleed air valve trip reset button. This can also be used to reset the air conditioning pack valves. Circled in red is the indicator lights. These will illuminate if the engine bleed air valve has been closed. There's one indicator light for each engine's bleed air valve. As you can see on the left side is for the port engine and the right side is for the starboard engine. This section will be looking at the 450 degrees Fahrenheit thermostat. This is highlighted in yellow. The thermostat is located in the bleed air duct downstream of the pre-cooler valve, as you can see highlighted in yellow. It's a direct acting bleed off bimetallic probe. It operates between 450 and 490 degrees Fahrenheit, regulating the temperatures. You can see a tube that is used to connect the thermostat and the control line from the 13th stage modulating and shut-off valve. On this slide, you can see the image on the left shows a thermostat on the engine, and on the right is a close-up. When the temperature over 450 degrees Fahrenheit is sensed, it will bleed off the control pressure in the sense line to the 13th stage modulating and shut-off valve and the 13th stage pressure regulator. As the control pressure reduces when an exceed in temperature is set, it will result in the 13th stage modulating and shut-off valve to modulate towards the closed position, which then reduces the amount of bleed air through the pre-cooler. Next is the engine bleed overheat thermal switch. This is highlighted in yellow, and it's located downstream to the pre-cooler, and it's used to protect the manifold from damage caused by overheating. In this slide you can see the engine bleed overheat thermal switch highlighted in yellow. You can see where it's located along the ducting on the leading edge of the wing. Here is a close-up of the engine bleed overheat thermal switch. It uses a bimetallic strip to detect the temperature. If the temperature detected exceeds 490 degrees Fahrenheit plus or minus 10 degrees for more than 15 seconds, then the bleed valve will close. This will protect the system from hot, overheated air. Here's another picture of the forward overhead panel. When the bleed valve is closed, it will illuminate the bleed trip-off lights that were mentioned earlier, but here they're highlighted in yellow again. The light can be reset, but the air temperature in the ducts will have to have cooled down by around 20 to 30 degrees Fahrenheit. The next component is the pressure transmitter. This is highlighted in yellow. There's one pressure transmitter for each engine, as you can see, and they're located downstream of the engine bleed thermal switch on the outboard side of the forward air conditioning equipment bay. In this diagram you can see the pressure transmitter in the air conditioning equipment bay. Here you can see the pressure transmitter. The pressure transmitter provides a pressure indication of the bleed air. Circled in yellow is a drain plug. The drain plug on the bottom of the pressure transmitter is used to collect moisture. If this moisture isn't collected, it could cause inaccurate pressure readings, or if the moisture freezes, it could cause the tubing to split. Next along is the ground pneumatic connector. This can be seen in yellow. There's one ground pneumatic connector, and it's located on the right pack bay area on the underside of the fuselage. You can also see on the diagram there's a check valve to eliminate any reverse air. Here you can see the ground pneumatic connector. On the right it's circled in yellow. On the left is the access panel for it. The connector is used to connect a pneumatic ground cart, so it can be used to pressurise the pneumatic system. This pressurised air can be used for starting, as well as using it for the air conditioning system when the engines are not running on the ground, although AC power will need to be available to do this. The maximum pressure for the ground pneumatic connector is 60 psig, and the maximum temperature is 450 degrees Fahrenheit. Downstream to the pressure transmitter is the air cleaner system. These can be seen highlighted in yellow. There's one independent subsystem for each engine, and it's used to purge the engine bleed air from any impurities. It'll operate automatically when engine bleed air is used for air conditioning and the aircraft is on ground, or when flaps are extended. In this slide you can see the air cleaner circled in yellow. This is an inline inertial type air cleaner. A purge line, which can be seen in red, as well as a purge valve highlighted in blue. This purge valve is electrically controlled and pneumatically operated. The air cleaner is lined with louvered lanes to collect impurities, which are highlighted in green. The air cleaner system works when air leaves the pre-cooler and it's ducted into the centre of the air cleaner, passing the louvered lanes to collect impurities, then to the downstream end of the air cleaner where heavier particles are collected in a collector ring. This collector ring is connected by the purge air duct through the purge valve, which then goes into the ram air exhaust duct. The ram air exhaust duct are highlighted in yellow. An air cleaner nozzle that's connected to the ram air exhaust duct is used to limit the amount of air vented overboard. Next is the isolation valve. This is highlighted in yellow. The isolation valve is located inside the keel beam with lightning holes for access. There's only one which will isolate the systems. The isolation valve separates air from the number 2 engine and the number 1 engine unless a crossfeed of bleed air is needed. On the left is a picture taken of the isolation valve, and on the right is a diagram from the aircraft maintenance manual. The isolation valve is automatic, motor driven, and is electrically controlled by a 3-position switch on the forward overhead panel. Here you can see the forward overhead panel with the 3-position switch showing close, auto and open. Usually the valve is in auto mode but can be closed or opened manually by the pilots using the open and close position on the switch. When the isolation valve is in automatic mode, it will be closed as long as both engine bleed switches and both of the pack switches are selected to on. On the left you can see the switch diagram showing the switch positions for the isolation valve, and on the right is a table that shows if there's any other combinations of switch positions, then the isolation valve will be in the open position. In the event of an engine shutdown or overheat trip, then the system will not automatically allow the remaining air source to supply both sides of the aircraft. Next we'll be looking at the pack valve, aka the PRSOV. There's one for each air conditioning system and they can be seen circled in yellow. The pack valve is located in the air conditioning pack, as you can see, and it's used to initiate airflow to each air conditioning system. It also regulates the airflow in cubic feet per minute, so a pretty constant flow is supplied to each air conditioning pack. As highlighted in the diagram, you can see the pre-cooled air from engine number 1 and 2 flow through the ducts, and before the isolation valve it takes a right into the pack valve. The air will then flow through the air conditioning after that. Here is a diagram of a pack valve with the actual valve circled in yellow. The pack valve consists of a butterfly valve, upstream venturi, pneumatic actuator and pneumatic controls. It's pneumatically driven and electrically controlled with a solenoid override for the APU operation. To open the butterfly valve, solenoid A, that's shown in yellow, will get energised to seat the ball on the vent port, which is shown in red. This will operate the actuator supply port, so the control orifice, that's shown in blue, and the actuator, that's shown in green, can be supplied with air pressure for the airflow control operation. The pressure is supplied from an inlet upstream pressure tap and is regulated by the pilot regulator. This is circled in purple. The air will pass through the control orifice and build up pressure in the actuator chamber. This will move the butterfly valve, that's circled in orange, to the open position. Here you can see the route that the air takes to open the butterfly valve. To close the butterfly valve, solenoid A, that's highlighted in yellow, will get energised and will need to seat the solenoid ball on the inlet port, that's highlighted in red. This will close off the actuator supply and vent it. The actuator spring, that's shown in blue, will then move the butterfly valve to the closed position. The APU operation, solenoid B, that's shown in yellow, will need to be energised so that the inlet pressure will act on the servo reset piston. As the piston moves, the venturi control balance is reset to control a high rate airflow which is needed if the APU is operating. When the airflow increases, the Venturi control servo, that's shown in yellow, bleeds off air through the bore valve to maintain the actuator pressure to maintain the flow. If the cabin pressure decreases, the bellows, shown in red, will expand and change the Venturi control servo spring balance, which will produce a low airflow rate. If there's electrical power loss, then the valve will open and will regulate at a constant pressure. Here you can see the switches on the forward overhead panel that control the pack valves. They're marked left pack and right pack.
On newer Boeing 737-200 models, the pneumatic ducts have gold paint or tape installation that has been added onto air conditioning ducts located in the underwing left and right hand pack bays. When the aircraft is on the ground in hot weather, it is very likely the air conditioning pact will be in operation using the APU bleed air. The gold paint or tape helps reduce radiation and reduces the chance of possible overheat warnings that may occur. These taped and painted ducts should be cleaned periodically to prevent a build-up of contaminants. The tape or paint should be cleaned with BMS 32 type 1 or 2 or naphtha, which are types of mineral and crude oils. They should then be wiped with a damp cloth. At normal temperatures, fire-resistant hydraulic fluid is safe with titanium. But if the temperature goes above 170 degrees Fahrenheit, which is 76 degrees in Celsius, the fluid turns acidic and starts to corrode the titanium, making it brittle. Titanium ducts are mainly found in three places: the air conditioning equipment bay, the wing leading edge TII system or the anti-ice system, and the pneumatic system just after the APU check valve. If we think any titanium ducts got contaminated with hydraulic fluid, we need to inspect them. Further information is found in Chapter 5 under Hydraulic Fluid Reaction with Titanium, Conditional Inspection. In the event of the insulation surrounding the pneumatic duct system suffering damage, it must be repaired. The maintenance manual conveniently includes the materials required for the repair. The following instructions have been provided in the Boeing 737-200's maintenance manual in Chapter 36.11.02. The area that requires the repair must be cleaned using a clean cloth that has been soaked in a mild detergent diluted in water. The area cleaned should then be rinsed with a second cloth soaked only in clean water and wiped dry. The insulation batt should be cut to an area that is at least 1.5 inches over the damaged area. The fiberglass film should be cut to a size that is approximately 0.25 inches larger than the insulation batt. Secure the insulation batt covered by the fiberglass film over the damaged area with silicone heat tape. The tape should then be applied around the duct, avoiding damaging both the repair and existing insulation. Thin-walled ducts can get damaged easily from bad handling, installation mistakes, or extreme operating conditions. Sometimes it's better to replace the whole duct instead of trying to patch it up, especially if pressure or temperature issues are involved. If there's a smooth dent that doesn't block airflow, you don't need to fix it. But for deeper smooth dents, you can remove them by pulling a ball mandrel through the dent, using a mechanical or hydraulic expander, or applying hydrostatic pressure while gently tapping around the dent with a non-metallic hammer. If you see shallow scratches, gouges, or corrosion less than 10% of the duct wall thickness and the damage is smooth and rounded, no rework is needed. For sharper damage, you can clean it up by removing nearby metal, but only if you follow these rules. The wall must stay at least 90% as thick as it originally was. Surface finish after rework should be 40 RMS or smoother. The slope should not be steeper than 1 to 10. Reworked curves must have a radius of at least 0.12 inches. If the damage is close to a welded joint, within 0.25 inches, special rules apply. If you can't repair the ducts within these limits, it has to be replaced. For badly damaged ducts, refer to the overhaul manual. You can temporarily repair a duct if the crack runs along the length of the duct. That's called a longitudinal crack. If the crack goes around the duct or if there are multiple cracks, you must replace it. If the longitudinal crack is less than 3 inches near a flange or pull-out, you can't use this method. Replace it instead. This method is just a temporary fix, and the duct must be replaced as soon as possible. To repair the cracked duct, you must stop drill the crack to prevent it from growing. Put a silicone rubber sheet over the crack, making sure it extends at least 3 inches past the crack. Place a stainless steel sheet over the rubber sheet. And finally, clamp the whole thing down with clamps every 1 to 1.5 inches and tighten them. To repair a duct flange, special equipment is required. This is known as the flange reforming tool. Specifically for the 737-200, Boeing specifies that you use the Adams flange spider. To repair the flange, you must get access to the damaged flange, use the flange reforming tool to reshape it, and if you can't repair the flange while it's still installed, you'll need to remove the duct first. Once removed, use the reforming tool to complete the repair. The duct ball joints are found in the engine sections of engine 1 and 2. They connect the 8th and 13th stage bleed manifolds to the engine bleed air and thermal anti-ice system ducts. Each ball joint has an inner bearing and a bearing nut attached to one duct, a retainer attached to the other duct, a replaceable wear ring, which can be split or solid, and adjustment shims. Maintenance on the ball joints includes removing and installing the wear ring with proper adjustment, doing a ball joint leakage test, and carrying out approved repairs if needed. If you find excessive leakage at the ball joint, you can fix it by doing these steps. To repair the ball joint, first remove the wear ring, check for any burrs or interference on the wear ring, the threads or the shims, and clean them up. Rework the rear wing, or if needed, replace it with an oversized wear ring to close up the end gap. When working with the wear ring, spring it in the gap until you get a 1-inch overlap, then let go. Do this a few times until the ring naturally sits together at the split. Reinstall the wear ring carefully. Start at the split and peel it onto the duct to avoid spreading it too wide. Finally, install the wear ring following the standard installation steps. This system is composed which work together to monitor bleed air pressure. Each transmit which is routed to the pneumatic manifold, just downstream of the bleed air heat exchanger. Both transmitters are electrically connected to a dual pressure indicator located on the overhead panel. One transmitter senses engine number 1 bleed air pressure, while the other senses number 2 bleed pressure. Each pressure transmitter features 2 ports. One connects to the pressure sensing line, the other is a vent to atmosphere. Located near these ports is a zero set hex nut. This nut there is no pressure in the ducts.
During normal operation, the number 1 engine supplies the left air conditioning system and the number 2 engine supplies the right. The reason systems are separated is for redundancy. The isolation valve allows cross-feed capability should bleed air not be available from one engine. Opening the isolation valve enables the functioning engine to supply bleed air to both sides, allowing continuous operation for essential systems, even if one engine bleed source is lost. The isolation valve can be operated manually or left in automatic mode. Engine bleed valves and the isolation valve feature manual override controls. Bleed air from the 8th stage reaches the main manifold via 2 separate ducts. One duct goes through the pre-cooler heat exchanger. The second duct bypasses the heat exchanger and delivers additional air directly to the manifold. Two separate ducts ensure that if the pre-cooler path is compromised or restricted, bleed air can still be delivered via the bypass duct, maintaining system functionality. APU also acts as a redundancy in flight by providing bleed air. During flight, APU operation has limits. It is limited to 2 starts per hour. Up to 10,000 feet it can be used to supply pneumatics and electrics. From 10,000 to 7,000 feet it is pneumatics or electrics. It cannot be used to supply pneumatics after 7,000 feet.
Prior to accomplishing troubleshooting on the distribution system, perform the engine bleed air compression control system adjustment test. Troubleshooting as necessary includes closing the circuit breakers. Reference to Chapter 21.11.00. After following the preparation test, perform engine bleed air distribution system test. Reference Chapter 36.11.00 to isolate problems in the system. Then perform the procedures on the following troubleshoot chart to isolate system and components faults. This slide outlines various troubleshooting procedures for the engine bleed air system. Each entry highlights a specific problem, probably causes, steps to isolate the problems, and recommended remedy. Addressing the shut-off valve overheat switch issues, isolating valve malfunctions, and check valve failures within the APU and ground pneumatic system. Each procedure following AMM references. In this slide, issues include check valve, faulty isolation or shut-off valve, and malfunction limit switch affecting indication systems. All checks follow AMM reference procedures. Engine bleed air pre-cooler leakage has been eliminated as a possible fault since any leak at the pre-cooler great enough to cause system problems should be obvious. Leakage from ducts may be determined by accomplishing duct leakage test shown in Chapter 36.11 Adjustment/Test. All troubleshooting procedures are based on the assumption that wiring is okay and that electrical power is available. If the corrective action in the procedure does not correct the problem, check wiring using wiring diagram. Prior to troubleshooting, check master dim and test circuit to ensure panel lights are operable. Thank you very much for listening to our presentation about the pneumatic system within the Boeing 737.